In the last video of this Acoustic Analysis for Drunks video series, I gave you some examples of how my room is better than yours. Ahaha, I'm just joking. Kinda. What I did was show you the before and after acoustic measurements of my current room. The point was to show you that I can get results. But of course, this isn't about me. This is about you. So in this video, I'm going to walk you through the Acoustic Analysis for Drunks worksheet. The purpose of the Acoustic Analysis for Drunks worksheet is so that you can understand acoustic measurements and take action based on that knowledge. Hey guys, I'm Michael Carrillo, aka Hex Spa. Welcome to my channel. I made a PDF which goes with this video series and this video in particular, so click the link in the description to download the Acoustic Analysis for Drunks PDF. Let's get into it. Let's take a look at the first step in this worksheet, measuring and drawing your room. The first thing you want to do is empty your room out so you can measure and draw it. This lets you have your dimensions on one page so you can predict your modes. Empty everything out, but your essential recording gear, desk, and speakers can stay. This will allow you to take a baseline measurement, give you maximum positioning flexibility, and allow you to see whether you're moving in the right direction. Here you can see my room. Nothing special. The front half is semi-square, and the rear is my kitchen. A small hallway bisects the space as a protruding mini-wall that has its own modal influence. From here, I'll add the dimensions. In this image, I've added my room's dimensions in centimeters. It's likely that the front of the room has more influence than the rear due to the proximity of the boundaries. Closer boundaries equals stronger reflections. We'll see later that the kitchen is pretty much irrelevant. Here you can see that the width, mini-wall, and height are nearly 1:1 or 2:1 in ratio. Classic bad dimensions. Not a perfect cube, but not ideal either. We'll see later how the axial modes of these dimensions bunch up around 70 Hz and 140 Hz. I didn't include the hallway width because A, it probably has minimal acoustic effect, and 2, I have to walk there, so it's not like I can treat it. Next, we'll multiply the dimensions to find out the wavelengths which will ultimately produce the resonant frequencies. Take your room's dimensions in centimeters and multiply them by 0.5, 1, and 2. This gives you the wavelengths of frequencies which will have peak SPL effects and ringing in your room. Knowing these are useful because you can target these dimensions when adding treatment to tame specific resonances. It'll also help you isolate surprises in your SPL response, which will likely be speaker boundary interference, or SBIR for short. Most of you can copy these ceiling values verbatim. 8 feet is an extremely common value in the US, and by extension, the modal response it supports. It's like chemistry. You know the solution, which are your room's modes. So when you add a chemical, which is the SPL measurement, you get the precipitate, SBIR. It's what's left over. The step that comes next is to convert these peak wavelengths to their much more useful frequency equivalent. Here are the frequencies at which we're likely to see peaks and especially modal ringing. It's important that you mentally cull unnecessary information to simplify the dataset. In this case, that means practically ignoring every value below 63 Hz and above your room's shorter frequency, which is usually around 200 Hz. The EBU recommendation I follow indicates that lower frequency boundary, and the upper value is where modal density is high. Visit the link on this page to correlate your wavelengths with frequency and write them down before proceeding. At this point, we have to predict our null response. This is very similar to what we did with peaks, but with different multipliers. To predict nulls, multiply your room's dimensions in centimeters by 0.25, 0.75, and 1.25. Once finished, move on to the next image. Just like with the peaks, convert the null wavelengths to frequency. You're focusing only from 63 Hz to about 200 Hz, but still figure out all the values. After this, we're going to find out whether or not our dimensions bunch up or balance each other out. As we'd expect from dimensions which are multiples, my room has bunched up modes. 70 Hz and 140 Hz are related, so it's no surprise that both ranges cluster. There's also null bunching around 90 Hz, 100 Hz, and 200 Hz. Sadly, none of these ranges really balance. I'll presently note that frequencies within the 100 to 200 Hz bandwidth are highly subject to SBIR. This is based on how far speakers tend to be from the front and side walls. Those influences will play into the actual SPL response we see later. By now, we're finished with the predictions and are ready to take our first acoustic measurement. If you're not yet familiar with the process of taking an acoustic measurement, please brush up on that so we can continue. When taking an SPL measurement, you initially see what the program has set as a default. But to clarify what you see, you want to smooth the full SPL. This takes away the jagged response from comb filtering due to reflections, as well as arrival time differences between stereo speakers. Importantly, you don't want to smooth the bass SPL. This is because sound behaves differently down low, and you want to see all the detail there. Right now, we just want to establish a baseline to see whether any changes we make are improvements or not. Another thing we want to do is to differentiate between our predicted modal response and what is likely SBIR. In this image, I've noted which frequencies line up with my predictions and which ones don't. There are several areas which are not surprises, but one in particular that is. This response has a severe null at 150 Hz, despite my calculation that the room's front width dimension should create a peak there. So now I have to take the next step and figure out what's causing that, since I don't want it in my response. Any frequency that is plus or minus 10 decibels from the reference level is potentially a problem. I say potentially because adding absorption should even out the frequency response to a degree. Even so, by figuring out the exact boundary that is causing the problem, you can specifically target it instead of just hoping for the best. That's what this whole video series is about, targeting problem areas through analysis as opposed to just sticking foam on the walls. Like I already mentioned, if it's not modal, it's likely SBIR. Therefore, to figure this out, we need to go in reverse order and convert the frequencies back into wavelengths. From there, we will apply the appropriate multipliers, depending on whether we are looking for the cause of a null or the cause of a peak. You need to go to the link on the null and peak frequencies image page to find the wavelengths of the frequencies in question. Your results will give you the distance from your speakers and/or microphone position that are likely contributing to each problem. Keep in mind that your speakers are in three-dimensional space. That means reflections from behind, above, below, and to each side will have an impact. Let me emphasize, maybe it's just me thinking that the side the speaker is on matters the most, but the other side matters too. Anyway, here I'm looking for the 150 Hz null. 150 Hz has a 228 centimeter wavelength. When I multiply that by 0.25, 0.75, and 1.25, I get 57 centimeters, 171 centimeters, and 285 centimeters, which is about 22 inches, 67 inches, and 112 inches. I was also having trouble with nulls at 175 Hz, 184 Hz, and 190 Hz with wavelengths of 198 centimeters, 188 centimeters, and 180 centimeters, all closely spaced. Rather than figure out each of those, and since they're all within 7 inches of each other, I just took the middle value and realized the boundary would be within 3.5 inches. I chose 184 Hz with a 188 centimeter wavelength. Multiplying that gave me 47 centimeters, 141 centimeters, and 235 centimeters, equaling 19 inches, 56 inches, and 93 inches. From here, I'll use a measuring tape to try to find which surface is causing me the grief. My philosophy is to go with nature. I apply this to acoustics from room selection through to speaker positioning instead of immediately resorting to EQ. Where possible, balance your response by moving the speakers in listening position to find the most even response. You can even measure each speaker individually so that a peak on one side is balanced with a null on the other, or vice versa. Though this balancing isn't always possible, always try experimenting with it before drilling holes for absorber panels or using EQ. Additionally, you should move the measurement mic in a reasonable radius from your chosen listening position to get a more complete impression of that spot. If you have a subwoofer, that'll interact with your satellite's bass response if applicable. So experiment with using the high-pass filters and other switches on all your speakers to get the best result. Do these things so that you're working from the strongest foundation possible. Regarding this slide, I treated this room several years ago, and I've made a few small tweaks since then. As a consequence, things have moved slightly. Despite this, The room's layout severely limits my positioning options, so my current arrangement is probably still very similar. We noted that the nulls from 175 Hz to 190 Hz are likely due to a boundary within 3.5 inches of 56 inches from the speakers or listening position. My front wall is 53 inches from the speakers. Bingo. Both speakers are being impacted by this, so it's no surprise that there's a big null there. This is a good example of bunching versus balancing. The speakers are also 59 inches from their closest sidewall and 113 inches from their opposite sidewall. 59 inches is within our 3.5 inch margin of error for the upper nulls, and 113 inches is 1 inch from where we expect a boundary to cause a null at 150 Hz. Obviously, an inch here and there is all within the margin of error, since the frequency wavelength chart is quantized to actual note values, and real life isn't. This is why you combine math with experimentation. There are almost too many variables and too few of us have laser-guided positioning. Use both and you'll be okay. The only thing left to do is add treatment. This isn't a series or worksheet about where or how to place treatment. That being said, I can give you a few ideas. Ultimately, your measurements will indicate which arrangement is best for your space and materials. In my case, being very limited by the room's features, the side wall ended up being where the absorbers were best placed. However, if you can, try to place panels wherever you reasonably expect that the boundary is exacerbating problem areas. Up until now, our predictions have helped us dial in the best placement for speakers, listening position, reflection-free zone, and speaker boundary interference response management. From here, we'll install those panels, take more measurements, and experiment, then move on to tackle modal ringing. Treating for specific modal ringing is as simple as adding absorption to dimensions which correlate. I focus on axial modes, just the resonances between two parallel surfaces, and I suggest you do the same. Tangential and oblique modes matter, but not to any degree that I've seen them prevent anyone from meeting the targets I've laid out. You can read more tips for adding treatment here on this image. They include gapping the panel 1x the thickness, angling the panel on flat surfaces or corners, adding foil reinforced craft paper facing to non-reflection free zone locations. That's basically just paper. You could use grocery bags. Targeting axial mode dimensions, and more. You'll know you're done once you've achieved 20 decibels of decay from 63 Hz to 200 Hz with an even taper to a longer decay at the bottom. This image shows what my decay looked like before I treated the room. You can see how the waterfall comes far forward. This is typical of an untreated space. Essentially, your speakers are in a crappy, resonant reverb chamber. The high Q peaks are classic ringing. Treatment will lower their Q and shorten the decay times. This is all reflected in the red and blue decay plot at the bottom, where the red is the initial response and the shades of blue outline the level between 140 milliseconds and 160 milliseconds. We can see a direct comparison of before and after here to see the result I ended up with. This is not a perfect response, but like I mentioned, I also built a recording zone and I did achieve the targets I'd set out to meet. Any room can be improved, but some have more potential than others. It's like Glenn says from Spectre Sound.
Is the juice worth the squeeze?
I met my targets, so I moved on. You can go as far as you want, but I found that acoustic treatment, like many things, has diminishing returns. Your results may vary. The last image I'll leave you with is 2 examples of excellent decay. The first room is a shed with thin, possibly plywood walls. The situation here is that if all the bass leaks out, it can't possibly resonate. So this is almost an anechoic bass response. The second example is a 1,500 foot cubed rectangular room with normal construction. Though larger rooms are a better place to start, this is proof that with enough absorption, you can still get a great response. Notice how both rooms have decay that's better than 20 decibels within 150 milliseconds and have a longer taper toward the bottom. This is what you want. All right, so that was a lot of information. If you're feeling overwhelmed, I understand. I once heard a jiu-jitsu instructor tell their students that if you can just remember 5% of what you learned or heard in class, that will develop compound interest over time. The key to understanding all this is just to go step by step. Try to understand why I put each step into the process. Make sure to post your measurements in forums where you can expect to get good feedback, like Ethan's Audio Expert forum. Or just give up. Save yourself while you can. Creating this video series took years of experience, and it's been distilled like corner store whiskey. Be sure to click the link in the description so you can download this PDF and use it as your reference. Acoustic principles are everlasting. What you learn here today will be with you for life. I've had my panels for 10 years and they're still going strong. Never needed a firmware upgrade. Never had any bugs. Hopefully you found this video helpful. Let me know what you think in the comments. In the next video, I'll show you examples of many ideas I tried and the acoustic measurements which go along with those. Often, when you're treating your room, you'll encounter surprises and challenges, and this room was no different. So I'll see you in the next video. Peace.